guys, let me welcome you once more in my channel, and let me appreciate you for stopping by to watch this video. If it is mathematics that you are looking for, I believe that you are in the right space. You are in the right place. Whatever you want to learn, we will get it right here. I believe that you are an aspiring mathematician. You want to know mathematics. I believe that after this video, whatever that you wanted to know pertaining the topic that is going to be discussed today, you will certainly know everything to do with it. You just sit back, relax, have your pen and paper, and participate and take notes. As you might have seen in the beginning of the video, that today we are doing logarithms, or there can be just simply called logs. So we'll be doing logs today. And I believe that you might be wondering, why are we doing logs as the video? Because logs are not even in the CAP syllabus as a topic there. But let me tell you that logs, even though they are not treated as a topic or not can be examined in isolation, you cannot have a question that is asking you about logs, but they are very applicable in mathematics, especially in CAPS mathematics, because if we apply logs when we are calculating n, when we are finding n in the financial mathematics question, and also when we want to discuss the inverse or find the inverse of a exponential function, you cannot be able to do so not up until you apply the logs. So that is why now we will be looking at logs, but we're going to just do a little bit of an introduction of the logs. We're not going to take everything, every details of the logs, but we're going to just give you the introduction, especially to the laws of logs that will be applicable now in finance and also in finding the inverse of a function, of an exponential function in particular. As I have mentioned to you earlier, that there are laws in logs that will be highly examinable, or you can use when you are doing your mathematics, your high school mathematics. For in the screen there, you can see a lot of rules. We're gonna take you through these rules as how do you develop them and how do you apply them. So that's what we'll be doing today. But let's start right from the beginning. Let's just look a little bit in the history and application of logs. Where are the logs coming from? So the logs are first appearing in writing from the writing of this guy here is called John Napier. So in his writing in 1614, where it is called Minifici Logarithmorum Canonis Descriptio. I'm not sure what language is this, but I believe it would be Latin, because most of the writing back then were written in Latin. So it was the first time that mathematicians learned having a form writing about the logs. Basically, John Napier was looking at how he wanted astronauts to do their work, because he is even quoted to having said, if you have the labor, then you can double the life of an astronaut. So Napier came up with another way of looking at exponents, so that is called logarithm. So that's what Napier did. So he wrote and published his work in this paper that is there in front of us. So let's look at how the logs have been developed and what is the meaning of these logs. Now let's look at some motivation of logs, something that will be very close to us as to why we are so interested in discussing the logs, or why the logs were invented in the first place. For instance here, if you can look at this question here, some of you have seen it already as from grade 8 or 9 when you were doing the exponential equations. And then the question there says solve for x if you're given that exponential equation 3 to the x is equals to 27. Now, how do you normally solve an equation like this, learners? You know already that you always must make the bases the same. Once the bases are the same, and then you can equate the indices. So now you can see there we are given 3 and there's nothing much that we can do about 3. And 27, in order to have 3 bases, both of these numbers, the easy way is to make both of the bases to be the prime numbers. This one is a prime already, so there's not much that we can do. But 27, or obviously, there is something that we can do. We can express 27 as a prime number to the power something. Obviously, that prime number that we have to look for, it should be the same as this one. So we have to find a number that we raise 3 with, and then we get 27. So the solution to this, as you can see there, 3 to the x is equals to 27. Now we can see that 27 can be expressed as 3 to the power 3, because 3 to the power 3 is 27. Now our bases, can you see, are the same. Then we can equate the indices, because this could be true if and only if also the indices are the same. So we can safely say here x is equals to 3 in order for this equation, the left-hand side and the right-hand side, to balance. Now, if we look at this one now, I think you also did this in grade 10, whereby you were presented with this kind of a case. If we look at this, we're having this number here, 3 to the x equals to 5. And now here we don't have the luxury that we had in the previous example, whereby this number could be expressed as 3 to the power something. Because if you look at it, both of these numbers are prime numbers now. So we're having a challenge here. How do you find the x value that will satisfy this equation here? So it's going to be a bit of a challenge. If we can look, because we've done this, if you remember in grade 10, we were doing some iteration. So we were looking and substituting some numbers. Most probably those numbers were rational numbers. In fact, they were decimal fractions, the numbers that could satisfy. What we used to do in grade 10, we used to do an iteration. We used to do some trial and error kind of way of finding the answers, because there was no really a kind of formula or kind of formal way of finding the solution to this equation. We'll try numbers, put numbers there up until we get something very close to 5. So how did we used to do it? Look at this now in our table. Let's say if we try x to be 1, then you can see there we're substituting 1 in the place of x, and then we have got 3 to the 1. 3 to the 1 obviously is 3, which is way too far from what we're looking for, which is 5. And then if we try the second number, 2, then there we have got 3 to the power 2, and 3 to the power 2 is 9, which is again a bit far, way bigger now than 5 that we're looking for. That means this number that we need to replace x with there to make the left-hand side equals to the right-hand side in this equation, it must be between 1 and 2. For argument's sake now, if we're taking 1, 5, and then put it right there, and then we have 3 to the power 1, 5. And if you just use your calculator, you could see that the number there is 5, 1, 9, 6, 1, 5, 2, 4, 2, 3, which is not too far from 5, but a little bit more. So our approach is mostly better if we approach the number from below 5. If we can get a number which is very close to 5, but less than 5, this one is above 5. So we can improve on the numbers that we are using on our iterations. So if now we try 1, 4, let's see what is going to happen. Now we're having 3 to the power 1, 4. And then if we press in our calculator, we get that number there. It's close to 5, but we have to have some differences there, because it's not as close as we would like. If we can get a number like 4,9999, we can say that number is the one that we can go with. In here, we still have 4,655536722, but it's a better estimate. But I believe that we can do better. So if we try a little bit more, looking at now another decimal after the second decimal after 4, we try 1,43 and see what is going to happen. and then we substitute, we replace x there for 1,43, and then we press that in our calculator, and then we get an even better estimate. 4,811532,175. But if we just fix our attention on the first digit, then we can see there is getting better. We're getting a number that is very close to 5. But as a mathematician, you would like to have something, if you don't get the exact, you would want to get something that is very, very close to what you are looking for. If we still continue, maybe try 1,45. And then if we substitute that number there, we're having 3 to the power 1,45. And then pressing that in our calculators, we get an even better number, 4,91842235, which is much, much better than all the previous estimations that we got already. 4,9 is very close to 5. Then if our question, our accuracy, we wanted to be accurate at least up to 2 decimal places, we will keep on changing this number up until we cannot get any number better than the one that we'll be substituting. So if we can try something else, because we can see that 1,45 gave us something very close to 5. Maybe still, if we maneuver this number, we can get even something much better. Then substituting that number there and pressing it in our calculators, we get 4,97, which is even better now, because the previous one, remember, it was 4,91. And this one is 4,97, which is even closer to 5 than the previous one. And we can carry on doing this, look if our attention is on the second decimal. And then now if we try 1,47 and we substitute it in there, and now we've got 3 to the power 1,47. What are we going to get? We're getting now something more than 5, a little bit more than 5. And we said earlier that our approach, we want the number that would be close to 5 but less than 5. So if now this one, 1,47, is taking us above 5, then we will abandon 1,47 completely. So we will stick with 1,46. If we have to go for the third decimal, then we're going to start looking at the numbers there at the third decimal, how close will it give us. So at the end of the day, when you are doing this, putting more decimal, you will be having 4,999999, but you will never get an exact 5. So it will be a number that will be very close. Just imagine, learners, you are at your work and you have millions of these equations like this that you have to solve. And I believe that it would take you the entire year trying to solve those equations. Hence, this smart guy developed logs to make life a bit easier than to have to do all those iterations to check which x value will satisfy the equation or will give you an answer where the error will be very small. So that's why now we are doing logs. Another motivation for the logs is this one here. Remember, learners, when you were presented with this, I believe that you know this formula, obviously, is the formula for finding the compound interest. This is a compound interest. When we are doing financial mathematics, it was easy for any learner from grade, let's say grade 10 all the way to grade 11. It was easy to find any of these parameters, A, P, and I. But to find the value of n, it came with another challenge, because it is not always easy to find the value of n, because this is an exponential equation, and then it's not always easy to make the bases on each side to be the same. So hence we will need the knowledge of the logs. So that was another motivation. So let's look at the logs and look at what is expected of us to do there. A natural way of understanding logs is better when you are discussing different representations, because mathematics at some point is the same thing, but we represent the same thing differently. Once we have that different representation, then you get some other interesting things that you can do with that representation, and that which becomes now another part of mathematics. For instance, we can look at this. I think all of you are familiar with 4 plus 4 plus 4 plus 4 plus 4, but it's tiring to write that down. And mathematicians said, okay, let's just find another way of writing this repeated addition. And then you can simply write this as 4, but how many are these 4s? They are 6. And then you can write that instead of writing 4 plus 4 plus 4 all the way, you could just write this as 4 times 6, which is much better. It's the same thing, but it's better. It saves you time when you are writing it, or obviously your pen as well. Again, if we have got a repeated multiplication, you can see that we have got 4 times 4 times 4 times 4. But how many are these 4s? Again, they are 6. There is another way that you can represent this multiplication. There it is. Then we call that one an exponential form. So we have got there 6 to the power 4 to the power 6. That's what we have. Instead of writing this long string of things, then we can represent this in a shorthand way by writing it in an exponential form, which is now 4 to the power 6, which is, these two are exactly the same thing. Now let's come to logs. If you have got 4 to the power 6, obviously the answer there is 4096. We can represent this answer in logarithm. So logarithm is another way, it's the same as exponents, but we're writing it in a different way. So how do we write it in logarithm? We say log of 4 or log base 4 of 4096 is equals to 6. So what is the relationship between these two? If you look at this, we have our base there, which is 4, and also in log, then the base for log is the same as what was the base in the exponential form. So we have got log base 4 of 4096 equals to 6. But how do you read this? Or how do we interpret this? In logarithm, we ask ourselves, what do I raise the base with to get this number? And the answer is 6. I'm saying here, you have to raise 4 by 6 to get this number. So that is how the logs, you can read them. The focus is always at the base. What number do I raise 4 or the base with to get this number? So always the answer is there. If you look at this, as I have indicated by using different colors, what was the exponent there in the log is the answer. What was the base there? In both of them is the base. So that is the key, learners, if you want to understand the logs. Now, let's get to the formal definition of logs. What are the logs? Let's just discuss the logs in their entirety. So this is the definition of a log. Remember, the logs and exponential form are more or less the two sides of the same coin. They are the same thing. It's just a different representation. The log and exponents are exactly the same. You must always remember. In here we have log with base a, x is equals to y. Now, if you have to translate this to an exponential form, it goes as follows. Now it's gonna be a, which was the base there, to the power y equals to x. So most of the time when I'm explaining this switch between these two, if for instance it is your equation is in logarithmic form, then the easiest way of doing this is just to take a to this side and push y. You can see there, push y upwards. You can see there you have got a to the y equals to x, and then x will be left there as the subject of the formula. So that is the easy way of switching between the two. If it is in this form now, you want to write it in logarithmic form, the key should be your base. You see, can you see your base there? Is the base there. So you say log of base a of x is equals to, what was the exponents, what was the index there? It should be the answer in the logarithm. So if you keep it that way, you will always get it right between these two forms. And then another thing that we need to highlight is the base here. For instance, now we have got two forms of logs. We have got this one, we call it a common log, whereby if it is not, the base is not written, we assume that the base is 10. This one we call it the common log, where the base is 10. And then we have got another type of log with is ln of x. This one is exactly the same as this one. It's just that the base for this one is the number e. I'm not sure you are familiar with that number, but when you get to university, you will know it's another number that falls in the set of irrational numbers. But when you get to university, you will learn more about the number e, and also ln is mostly used at university than in high school. But these are exactly the same thing. It's just that this one is of base 10 and this one is a log with base e. Now let's look quickly on how do you switch between the logs and exponents. Let's look at these following two examples that will show us a quick way of switching between the two, which is very important in understanding the logs and exponents. Now we're having this question here. Write down 2 to the 5 equals to 32 in logarithmic form. So it is easy, learners. This is how you're going to do it. Remember, the key here is the base. The base is 2 in the exponential equation or in the exponential form. Same applies in a logarithmic form. That base is still the base in the logarithmic form. So in the logarithmic, what do we say? What do I raise 2 with to get 32? And what was the exponent there is an answer here. So that's how we would write this same thing in a logarithmic form. And now the second example, or the second question, is asking us to write this is in a logarithmic form. We write it now in an exponential form. What do we do, learners? Remember what I have indicated or tipped you in the beginning, that the easy way of switching here from the logarithmic form to the exponential form is to just take this base here and take it to this side and push the 4 upwards. Then you'll be having 81 is equals to 3 to the power 4. As you can see there in the screen, 2 to the power 4 is equals to 81. So also this one is easy to do the switch between the two, the logs and the exponents. There we were switching from exponential form to logarithmic form. Here we are switching from logarithmic form to exponential. In the same manner, if we now continue and discuss the laws of logs, which most of them you're not going to use in your entire metric syllabus. Some of them you will see them in varsity, but we're going to just give you a summary of all those laws and indicate to you those ones that are applicable to you. So the first law of logs is this one here. If you have got a log, remember you have got, it is base A, and then you have got a product. The log of the product is the same as the log of the sum. So for instance here, log of with base A of xy, you can rewrite this as log base A of x plus log with base ay. So instead of now having x times y, you can have a plus. So remember, what is the key here? The bases need to be the same as the original log. So that is law number 1. Law number 2 is about the quotient now. If you have got a log with base A of the quotient, you can write it as a difference. So for instance here, log of A, log with base A of x over y, you can rewrite this as log with base ax minus log with base ay. Again, we retain A, the base as A in either situation. So it must never be a situation where now you change the bases here. They must have the same base as the original log. Then the following law, law 3. This one, learners, you need to take hint of it because we're going to use it when we are solving financial mathematics. We're using this one more often. So just make sure that you write this one down. What does this law say? It says that if you have got log with base A of x squared, something to the power something. So what is the advantage that it is giving us? We can always take the power to the front. And then now we're having n log base ax. Can you see the power that it gives us here is to make now, instead of having this as an exponent or an index, then we can take it down to the front. So this law, you must always remember, learners, is very important law in the logs. And then now we have law 4. This law is called the change of base. If you're having a log being written like this, you can change the base here. How do we apply that? We can say is log with a different base now, b, x, with the x that we had there, can you see, is there now. All divided by log with the same base, b, of a. And this a here, that was what was the base there. So we call this one, this law is the change of the base. So maybe in another video where we will be looking closely on the logs, doing some exercises, we will touch on this. I will do that video only for those people who want to know more about logs, but nobody will ask you in the examinations, in CAPS syllabus, about the use of all these laws. The one that I highlighted to you is this one here that you need to know. Remember, from the definition as well, you needed to know that switch between exponential function and logarithm. So don't worry about all the other laws. You will just know them or get the application of these laws when you're getting to university. And then we have got what we call deductions. So we have got two deductions in terms of the logs. The deductions are the things that comes obvious, that because we already discussed the formal definition. So the deductions, they don't need us to prove anything. They just become obvious. So the first deduction is this one. If you have got log with base a of a, so the answer is always 1. Why it is so, learners? Because we are asking ourselves here, if you remember well, when we are discussing the definition, or how do you read the logs or this information, we say here, what do I raise a with to get an a? Obviously, there's no other way. You have to raise a with 1 to get an a. So that is becoming obvious. So what is important about, what is it that is so important about this, learners? Remember, if you have got a log with base of the same thing as the base, the answer is always equals to 1. We need to remember that. Secondly, is this second deduction here. If you have got log of base a of 1, then the answer is always 0, because remember, again, the interpretation of this, we asked ourselves, what do I raise a with to get 1? That a could be any number. What do I raise this number with to get a 1? Obviously, we know from exponent that it is only 0. With any number that you raise by 0, the answer is always equals to 1. So those are the deductions, learners, that you need to remember when you are dealing with logs, even though this deduction also may not feature in the examination or any of your examination, but it is part of logarithm, part of the things that you know if you want to understand logs. Now, with all that having been done, I believe that you understand the logs. There's nothing that can really defeat you when it comes to log, when it comes to the examinations. So that was all the minimum knowledge that you need to know about the log. So keep this information close to your heart, because in our next video, we'll be discussing the inverses. Particularly, this kind of information is going to assist you when we are discussing the inverse of an exponential function. So I believe that you will watch this video and the following video when we are discussing the inverse of the function, the inverse of an exponential function. So we will apply these laws of logs. Then when we are there, let me see you when we are dealing with that part of mathematics. Just keep on watching and following this this channel, because there are many great things that we're going to do in here. And most importantly, you must remember, you must always like the videos and share them with your friends and peers. Thank you very much. Till we see each other again. Thank you.